Hello everyone, I'm Ankur from CQuERE and today I'll be talking about the physics of singularity. This will be a rough overview about black hole fundamentals. So let's start. So, what is a black hole? A black hole is often misunderstood, but it's not something very tricky. Uh, uh, Sir Albert Einstein proposed in his theory of general relativity that the space-time gets curved around masses or energy densities. So, uh, gravity is just a different manifestation of that. So gravity is actually the curvature of space-time. And if the mass of an object gets sufficiently dense, then the space-time can get curved in a way such that even light cannot get out of gravity. So that then in that scenario, that object will be totally black because no radiation will be coming outward. So that's why it's called a black hole, and that's how it gets formed. Normally, after a supernova or collision of two stars or neutron stars or merging of two small black holes can create a black hole. So yeah, and black holes have several parts of it. Firstly, the singularity, or the center of the black hole, where the mathematics break down. The relativity cannot predict what happens at that point, and yeah, so that's called the singularity. The theoretically the density gets infinitely dense. So yeah, and also there is the event horizon. Event horizon is a place where that is the boundary, that is a horizon that if you cross the event horizon, you will not be coming back to the known universe outside the black hole. So yeah, event horizon is the one way valve. You can say that if you go to the other side, then you will not be coming back. And then there is the photon sphere. Photon sphere is nothing but light waves or light particles or photons traveling around the black hole. They are revolving around the black holes on a spherical path. So yeah, and also there is an ergosphere. Ergospheres are caused by rotating black holes, which are normally found in our universe. And rotating black holes are also called the Kerr black holes. And ergosphere is nothing but when a rotating black hole is so massive, and it actually the space time around it gets so curved that they actually kind of rotates alongside the black hole. So that's the place where these space time thing happen, and that is called the ergosphere. And there is also the accretion disk. Accretion disk is nothing but superheated gas and dust. They are spiraling inward the black hole, and the accretion disk actually emits bright X-rays, and we can observe black holes because of these accretion disks. And also, this is a fun thought experiment. If there are two person, Alice and Bob, and one of them is very distant from the black hole, and the other one is falling inside it. So, if Alice is a distant observer and Bob is falling in a black hole, then Alice will observe that Bob is slowly getting redshifted, and Bob is getting slower and slower, and at the event horizon, Bob has stuck. Bob will not cross the event horizon for Alice. Alice will see that Bob has stuck at the event horizon forever. And on the other hand, Bob uh, will not feel stuck at the event horizon. He will see that he's falling inside the event horizon, and he will not feel anything about getting stuck at the event horizon or anything. But the fun thing is the tidal force is so highly gradient at that point that before even crossing the event horizon, Bob will get smashed, and he will get spaghettified. So yeah, Bob will not be living when he's crossing the event horizon. So yeah. Also, the black holes are pretty interesting because of the singularity, because we do not know what actually happens inside a black hole at the singularity. The metric given by relativity, if for a non-rotating non-charged black hole, it's called the Schwarzschild metric. For a rotating black hole, it's called the Kerr metric. There are also different metrics for different types of black holes with charged black holes and all. But those metrics, they cannot give account for the singularity, the point of singularity. And the metrics simply blow up. They give some undefined parts, and we still do not know how to solve them. Quantum gravity can be a bridging theory that bridges quantum mechanics and gravity, and that may come handy solving these problem. But we are totally clueless about quantum gravity at this point. Also, the mass of a black hole is pretty interesting, and black holes can be classified. You can classify black holes according to their mass. So, stellar mass black holes are basically small black holes, and they're roughly around 3 or 100 solar masses, and intermediate mass black holes are of 100 to 100,000 solar masses. A supermassive black holes normally ranges between millions to billions of suns. So yeah, but the density of a black hole is pretty interesting. It actually gets less when you increase the mass, and the relation is written there. It's 1/mass squared. The density is proportional to. So the graph is given, and a fun fact is a supermassive black hole like M87. It has an average density that is comparable to air or water. That's pretty fascinating. Also, there is another thing called the Hawking radiation, that black holes are not totally black. So they actually radiate some energy, and that is called Hawking radiation. So to understand Hawking radiation, one needs to know that there are vacuum fluctuations, that is particles and antiparticles. They get created at vacuum points, and they get annihilated after. So near the event horizon, if such a particle and its antiparticle gets created, and the antiparticle gets sucked in by the black hole, and the particle gets released, so then the mass of the black hole will get reduced, and we will observe the particle released as some radiation that is getting emitted from the black hole. So this is called the Hawking radiation, and because of it, we can say that black hole can get evaporated, and also we can assign some temperature to a black hole, and this fact gives rise to black hole thermodynamics, that black hole can have some entropy. And this is a schematic diagram, that the temperature is inversely proportional to the mass of a black hole. So a small micro black hole, it has a temperature of 10 to the power 12 Kelvin, that is very hot. And a stellar mass black hole has temperature of 10 to the minus 8 kelvins, and supermassive black holes have temperature of 10 to the power minus 14 kelvins. So also the lifetime also gets increased with mass, and it's actually proportional to the cube of the mass. So a micro black hole lasts for a few seconds. A stellar mass black hole has a lifetime of 10 to the power 67 years, and a supermassive black holes, it has a lifetime of 10 to the power 100 years. So yeah, that's pretty large. Also, there is a paradox called the information paradox, that if a black hole, uh, suppose Bob gets sucked in by the black hole, and that black hole gets evaporated and totally. So will the information that was sucked in by the black hole, will that be gone? The answer is no. That cannot happen. That's a paradox. So to solve this paradox, we have a theory called the holographic principle, that all the information that gets sucked in by the black hole is actually on the surface of the event horizon. We just need to decode it and find the relevant parts of the event horizon. And yeah, so this is also pretty related to the thermodynamic approach of black holes, and this gives rise to the black hole thermodynamics. In classical thermodynamics, there are quantities like temperature, energy, enthalpy, entropy, and the second law states that the entropy will never decrease with time. And black hole mechanics, it gives surface gravity, mass, horizon area, and also the area theorem. And horizon area means the surface area of event horizon, and area theorem says that the surface area of event horizon will not decrease with time. So there is a one-to-one correspondence between the surface area of event horizon and the classical entropy that we see in classical thermodynamics. And with that observation, the Bekenstein-Hawking entropy formula is made, and it states that the entropy of a black hole is actually proportional to the horizon area, and the proportionality constant is kb by 4 lp squared. KB is Boltzmann constant, and LP is Planck length. And there are also some observational evidence. Obviously, the gravitational waves, it got discovered by the it got observed at the LIGO observatory centers. And yeah, so there are also the image of a black hole that got captured in 2019, and it was revolutionary. And also the structure of galaxies, especially spiral galaxies, that they are rotating some huge massed object at the center of the galaxy. And uh, that proves that some hugely massed object is at the center of that galaxy, and normally that is a black hole. And there is a picture of a stellar system orbiting a black hole called Sagittarius A. Also, concluding, we have general relativity, we have quantum mechanics, and we are still clueless about quantum gravity. So there is the geometric part of a black hole that comes from the general theory of relativity and the Riemannian geometry. There is the thermodynamic part that comes from the information theory, and also there is the quantum mechanics part that comes from the Hawking radiation, and yeah, so all those things. But as we are totally clueless about the theory of quantum gravity, we are still unknown to singularities, and we still do not know what happens exactly at the center of a black hole or even inside the event horizon. So yeah, that's something we are working on at this moment, the theoretical physicists. And yeah, I hope that within a fair amount of time we will have a theory for quantum gravity. Thank you.